in today's session, we'll look at various security protocols and how it evolved over the years, right? And we all think that security is important. I hope you all believe that security is important as well. But if you don't, here is a quick demo for you. I'd like to demonstrate this demo. Let me open Wireshark. And I'm sniffing on my Wi-Fi interface. And I'm interested to see the HTTP traffic. Currently, I'm connected to an open network, that is no security, just open authentication, right? And let me browse one of the HTTP websites. Okay, and here let me enter my credentials, right? Let me give HTTP as username. Yes, let me do a login. So my laptop Wi-Fi interface has captured some information, and here you can see the post data that is going from my laptop. See, oh no, you can see my password which I have entered, right, unencrypted. Even though it is not visible to all of you guys while I'm entering, Wireshark has the potential to capture. Why? Because I am connected to an open network. Though it's on my laptop interface, you could actually see this data over there if you sniff, because since I connected to open network. So I feel now I'm in a big risk, and I hope this session by Sitarama sir can help me in understanding how we can avoid these risks. So with that being said, I'd like to hand over to Sitarama sir to get some insights on Wi-Fi security.
So let's get today's session started. Thank you all for joining. We're all excited about module 4, which is about security. So today we'll introduce the various security protocols, as Sainan mentioned. As you just saw, like if you are trying to log into a website connecting to an open network, this could happen to you in an airport, it could happen to you in a hotel room, wherever you are. If you're trying to connect an open network and let's say you're trying to access your bank account, you're typing in your username, password, and there could be a hacker right next door who is just opening up Wireshark, sniffing that information, and seeing the passwords in plain text. Of course, there are securities built into the browsers that we all know of. If you're using a more secure browser, then you might not have this issue. But in certain cases, you might be able to see these passwords in open air, and that is a huge problem. It is scarier than we think, right? And this is the reason why security is extremely important. So before we jump into today's session, let's just quickly recap what we talked about in module 3. As Sainan summarized, we went through various aspects of wireless LAN MAC layer. We started from the basics of AP management, control functions, beaconing, talked about active scanning, passive scanning, basic service sets, system capabilities, and so on. We went into detail about MAC framing, headers, the key functions of the MAC headers. We talked about the different header formats for management frames, control frames, data frames, and we talked about frame controls, 2DS, FOMDS bits, retry flags, all kinds of header information, address fields, and so on. We went through that in a lot of detail. And then we went into carrier sense medium access. We talked about how Wi-Fi accesses the medium. We said how Wi-Fi is different from cellular, where we are not using deterministic time slots. We are sensing the medium and checking the medium is available. And when the medium is available, we transmit. But for that, we use a collision avoidance mechanism, which uses concepts like random backoffs and interframe spaces and so on. And we explained how QoS works, EDCA parameters work, how interframe spaces help in creating priority access to the medium, and so on. In the last session, we talked about data transfer, and we explained the concept of overhead and how they could be more than 90% overhead in the wireless link when you're trying to send data, because of all the management, control, carrier sensing, back off, all these other things. And then we explained how as the standards evolved, there was no more need for speeds and feeds as opposed to reliability. And so people wanted to transmit faster, they were transmitting at higher data rates, and so they want to send more information in a small amount of time. And from there came aggregation. We explained the concept of aggregation, where once a transmitter gets access to the medium, they can burst and send lots of data right next to each other, and then wait for what we call as a block acknowledgement, where lots of data frames are acknowledged in one shot. We also talked about admission control. How can you make your wireless LAN cell more efficient by not admitting devices when you're not supposed to admit them, and so on. We went through that in detail. So module 3 covered a lot of ground. There are 4 sessions there. All 4 recordings should be available on the website. We are a little bit late on finishing up the notes, so please bear with us, and we'll upload the notes as soon as it's available. But the videos should all be up there, and you can go watch them for all 4 sessions. So module 4, as we promised, we're going to talk about security. We're going to start with the basics of security and various security protocols and how they evolved. And then we're going to dig deeper into the next section. We're going to dig deeper into authentication and encryption mechanisms. We talk about the various EAT methods, key generation, and so on. And the third session, which I'm quite excited about, is about attacks and vulnerabilities. So we're going to talk about different types of attacks that are normally happen in the Wi-Fi world: DOS attacks, man-in-the-middle attacks, cracking security keys, and what mitigations have been applied to actually take care of these attacks, and what kind of attacks have been found in the industry. We're going to talk about that. In the last session, we'll talk about seamless connectivity. This is not completely related to security, but seamless connectivity is important as you move from one network to the other network. And sometimes your device might be handing off from let's say a cellular network to a Wi-Fi network, and as you go from your house to a coffee shop to driving on the road and so on. So the device might not know, but it might be switching between different carriers and different cellular networks and Wi-Fi networks, and the security context has to be moved from device to device without any loss of security and without loss of connectivity. So how do you do that? How do you use various security mechanisms that are based on SIM authentication and so on? So we're going to talk about that in the last session. So those are 4 very important topics when it comes to security, and a lot of detail that's going to be in the next 4 sessions. We are very excited about that. So let's get started with the session 1 in module 4. So before we get into all the technical details, let us basically set some context here, and let us look at the various methods that we're using to connect to a Wi-Fi network. We all know this, even if you're new to Wi-Fi, you should be knowing this. So one of the most common methods that we use is we find an open network. Let's say I am walking in the shopping mall or on the street, or I'm sitting on the park or something like that, and I want to connect to the Wi-Fi network, and I find an open Wi-Fi network and I connect to the network. Right, so it's the most common thing. It can be quite scary, but a lot of us are guilty of doing that, and we find open networks. And if you get free internet connectivity, why not connect with it? A lot of us do this, right? So this is one of the common things we do. The other thing we do about how we connect to a Wi-Fi network is we connect to a Wi-Fi network in our home. So for that, we normally use some form of security. So let's say this is your home router. So this router, when you log into this router, we're going to type in some form of password, and then the device that connects to the Wi-Fi router also needs to have the same password. And if it has the same password, then it can connect to the Wi-Fi network. So let's say you have a guest in your house, someone is visiting your house, your friend will say, hey, buddy, what's the Wi-Fi network password? And then you'll give them the network password. They're going to type it into their device, and then they'll connect to your Wi-Fi network. So there is one level of security, so that you're controlling who is connecting to your network. But that's one method in which we can connect. Another method which we connect to Wi-Fi networks is when we are out. Let's say we are going to basically a hotel, and we're staying in the hotel overnight, or a restaurant, or some place like that. When you connect to the Wi-Fi network, the Wi-Fi network is open, so you basically connect to the network, and then when you try to browse the internet, it redirects you to a web page. Most of you might have seen this, and then it'll ask you for information like what is your name, what is your room number if you're staying in the hotel, so that they can check that you are a valid guest that is staying in their hotel. So what they are trying to do is they're only trying to make sure that you are a valid guest that's accessing the network. They're not trying to secure your connection. So which means that once they validate that you're a valid guest, and you put in your name and you put in your room number, and that matches their records, and then you hit connect, they'll allow you to connect to the network, Wi-Fi network, and your connection is still open. Right? So they don't care if your passwords get hacked or someone steals your bank account information. They care about making sure that the right people are connecting to their network, right? So then it's still a problem, right? Security is still an issue there. Same case with the airport. If you're connecting to a free airport Wi-Fi network, normally they have this big terms and conditions and big disclaimers that say you're connecting to insecure network. Anything that happens on the network is your own responsibility, and so on. So there's again very little security in that area on the Wi-Fi space. And then one of the other common methods we use is how we connect to the Wi-Fi network in our offices. This is probably the most secure method. And when I bring my laptop or my phone into my office, and when I log into my laptop, most likely the laptops and the devices that are issued to me are already issued by the IT team, and the IT team already puts on some certificates, some credentials on the device itself. And they will, in many cases, they will connect it to our Active Directory services or some form of mechanism where they can authenticate you on the network. And so when you bring in your laptop into the company network, and then you type in, you basically connect to the Wi-Fi network, you log into the access point, you'll automatically connect to the Wi-Fi network, and that connection is secure, and it uses something called as enterprise Wi-Fi security methods, right? And that is based on usernames and passwords. So that's probably the most secure way of connecting to the Wi-Fi network. All of these methods, a lot of things are going underneath, under the underground when we actually connect to the network. And what's going underneath is what we're going to discuss in this particular session. Okay, moving on to the next slide. So let's say talk about how do you secure communication. So let's take a very simple example. Let's say there are two people, Chris and Rob, and Chris and Rob don't know each other. So Chris's boss wanted Chris to deliver some message to Rob, right? But and so he sent Chris, and but Chris doesn't know who Rob is, and Rob doesn't know who Chris is, right? But they need to communicate with each other, right? And that's the challenge. So how do you secure that communication, right? So there are two aspects to securing the communication. First, Chris needs to know that Rob is the right person he needs to communicate with, and Rob needs to know that Chris is the right person he needs to communicate with. So which means that they need to mutually authenticate each other, that they are the right people. So one method you can use, you might have watched this method in old movies, where basically the original person who wants Chris and Rob to talk to each other would have taken a let's say currency note and tore it down into two pieces and gave one piece to Chris, and then given the other piece to Rob. And so Chris has his piece and Rob has his piece of the bill. And now Chris can bring that bill to note to Rob, and Rob can bring his to Chris, and then they'll put it together and they will authenticate each other. And it basically, once you put the two pieces together, it will look like a full currency note. And then now Chris knows that Rob is the right person, Rob knows that Chris is the right person. So first step is they need to authenticate, and they use some method. We are just using this as an example. Okay. So once the authentication is done, the next point is Chris needs to deliver his message to Rob. And so Chris can say, let's say the message is that we need to launch attack tomorrow at 6 p.m. right, on our enemy. Right. So Chris can say that in open air and say, hey Rob, the message is that we're going to launch an attack on our enemy at 6 p.m. Instead of doing that, Chris can speak in some form of a code language. Right. In this case, Chris is saying the watermelon has arrived, and Rob says, yes, it's time to make some juice. Right. And then we have our intruder who's sitting here, and he's trying to understand, what are they talking about? I don't understand what they're saying. Now, what Chris said, Rob understood, and what Rob basically understood, Chris understood that Rob understood what he was trying to say. And they are able to communicate with each other in coded language, and the intruder is not able to understand what they're saying to each other. This step is called encryption, where you're taking some plain set of information that anyone would understand and encrypting it, and basically communicating using some of a sign language or a code language, which the other person does not understand, and only these two people understand. So the two essential steps to secure a communication would be authentication, to make sure that they are the right people talking to each other, and then there is encryption, where once authentication is done, the communication has to be encrypted so that the third party or a third person cannot understand what you're saying. So if you look at how this works, and there are many examples in history. Now, if you're talking about a normal Wi-Fi network, if someone hacks your password, then it's just a matter of they actually finding out your password and log into your network, and you might be able to solve the problem one way or the other. But the real big advantage of encryption and security is in the war zone, right? So especially during the World War II, World War I time frame, authentication and encryption were extremely valuable, because always these commands would come from if you take during Nazi Germany, World War II, the leadership would actually send very cryptic information, or information that is supposed to be very secure, to the soldiers in the battlefield, and they want to encrypt that information so that the enemy's engineers or people are not able to find out what's going on. So let's say they are going to talk about war tactics, or what they're going to do is the next step in the war. They need to encrypt the information. So in the olden days, this was many decades ago, there was this, as an example, there was something called as an Enigma machine. It's actually quite fascinating. You can find some nice YouTube videos on this one. I was watching one the other day. But it's a very kind of a very physical analog device. It has a bunch of buttons. So what it does is it has like 26 buttons that represent the 26 letters, alphabets in alphabets here, and you can push any alphabet, any button here, and it will light up a different button, right? So for example, if you push on A, it might light up Y, right? And that's your code. For the plain text letter A, your code is Y, right? And if you type B, maybe it'll light up like C or something. So the code for B is C. Like that, you can type in plain text one letter at a time, and it will give you the coded text. And then that coded text, or the ciphertext, is what's transmitted or sent to from point A to point B. So while you're coding the text, you also enter a key, which is basically a series of bits or a series of digits. And when you enter that key into this box, the key is used to actually encrypt that plain text into coded text. So on the other side, on the receiver side, the receiver also needs to have the same Enigma machine, and they need to get the same key somehow. And the key is sent using some other method, so some other transmission method. So if the receiver has the key, and if they have the encrypted text, then they could do the opposite. So that they can type in the encrypted text like one letter at a time, and then that will output the plain text, and then they can read the plain text from there, which is quite fascinating how they do that. And that is a very primitive early version of implementing security, where you can use the concept of keys to take some plain text and create an encryption text, and then send the encrypted text separately and the key separately, so that the receiver, once they get both those things, can then decrypt and get the information right back. So this is just an example of how an Enigma machine works. You'll find lots of interesting videos on that. So let's get back to like what we refer to as the 3 pillars of Wi-Fi security, the 3 basic things, right? So let's say the first one, of course, is authentication. So let's say Alice is the sender and Bob is the receiver. They have to first do authentication. So Alice checks if Bob is the right person to deliver the package to. So Alice has a package to send to Bob, and Alice checks if Bob is the right person to deliver the package to, and Bob checks if Alice is the right person to take the package from, right? They need to mutually authenticate each other. Otherwise, there's a big problem, right? So that's step 1. And then, of course, we talked about confidentiality. So Alice gives package to Bob in a locked box, and only Bob has the key to open it. So which means that information is sent in an encrypted fashion using a key. And once Bob receives it, only he has the key, so he can decrypt it and get the information. And some other person, Rob or Chris, don't have the key, so they cannot decrypt that information. They cannot read the information. So confidentiality is the second pillar. The third pillar is the integrity of the message. So Alice is sending a package to Bob, and the package should not be tampered with. The package received by Bob should be the exact same package that Alice has sent, and that information cannot be changed. So if you encrypt the information and you decrypt it properly, but the actual information itself got changed, then that is a big issue, right? So integrity is also, message integrity is also important. So these are the 3 base components of security. One is authentication, confidentiality, and integrity. And all three of them have to be working well to actually have a very secure communication. So now let's talk about the what I'm referring to as the three enforcers of security, Wi-Fi security. So who are the policemen? Who are the ones who are making sure that security is actually implemented in a Wi-Fi network? So there are three entities that we need to know about. One is basically the supplicant. Supplicant is basically you can consider it as a piece of application or software that runs on your endpoint. Let's say in this case on your phone or your laptop or some device like that, and it does the user side part of the encryption and authentication. So the authentication encryption portion, there has to be user side portion of it, and that is done by the supplicant software that is running on the device. And then there is the authenticator, which is in most cases the access point, right? And the access point is acting as authenticator, which is basically doing the authenticator function. And then there is also a third entity called the authentication server, which is some entity on the network that is also participating in the authentication process. Now, if you're looking at residential Wi-Fi networks, like a residential Wi-Fi router that we have here, we only need these two entities. So basically, we need a station or a client, and we need an access point. And this is basically the supplicant, and this is the authenticator, right? So all you need to do is you need to manually enter a key. So let's say there is encryption or security enabled. So you can enter a key in this device. You log into this device and you enter a key. And then you log into this device, you enter a key. And then you can connect this device to this device, and then they can both communicate with each other. They can authenticate each other, and also they can encrypt the information using that key. So that is how residential Wi-Fi works, right? So every access point has its own set of keys, and every device connecting to that access point will use that key. So if you are in your house, you might have a certain password to connect to your Wi-Fi router. If you are in your friend's house, there might be a different password to connect to their Wi-Fi router, which you will again manually enter into your device. So that's how residential Wi-Fi security works. But if you're in an enterprise, right now I'm in my office, and we have like a 5-floor building here, and every floor has several access points, and they're all advertised in the same network. So if I have this my device here, and if I want to connect the same way as I would connect to in my house, as I move from this room to the next room to the next room, every time I'm connecting to a different access point. So if each access point you manually enter the keys, then there might be different keys for each access point, and that's a big problem. I have to enter different keys, and I have to manually connect to each access point of the network. So rather than authenticating with an access point, because there are many access points in this network, I would authenticate with a even more central entity, which is behind all these access points, which is called as the authentication server. In some cases, you call it as the radius server or ACS server. All kinds of authentication encryption is done. Authentication is done by a server on the network, and the server has a global visibility of all the access points and all the devices that are on the network, and that's called the authentication server. So if you're doing enterprise security, you will need all three: supplicant, authenticator, and authentication server. If you're doing residential, you only need these two components. And we'll come back to this in more detail in the next session and explain that. I just wanted to give you a big picture here. So again, coming back to how personal and enterprise security works, if you're doing personal security, then you manually enter the keys. There's only the Wi-Fi router, and there is a mobile device. You manually enter the what we call as a pre-shared key, a key that is shared ahead of time. That's why it's called a pre-shared key. And you would enter the key here, you would enter another the same key here, and then they'll communicate with each other. And once the connection is done, then you get access to the internet, right? And as I mentioned before, if you're doing enterprise security, then you have other elements also. You have multiple access points, you have a wireless LAN controller, you have an authentication server, typically a radius server, and then there is a whole authentication process that happens between the device, the supplicant, and the authentication server. And the access point is acting merely as a relay. It's only relaying the information. It's not doing the actual authentication, but it is relaying the information between the supplicant and the authentication server through the network. And enterprise security is more involved, and it has lots of really cool features and things like that, which we will talk in the next session. Okay, so now now that we painted the big picture, we talk about the pillars, we talk about the enforcers of wireless LAN security. So let's come to come back to the basics. So if you look at the base WLAN standard, 802.11 standard, it started off with what we call as open authentication. We all saw that in the last module. We talked about how open authentication works. A client sends an authentication request to an AP saying that it's using an open authentication mechanism. The AP says, okay, fine, you're using open authentication, and I'm also using open authentication. So we know about the risk. So, and it will send an authentication response, and the client will connect, and then data transfer will start. So this is kind of the open system authentication that we are using to connect to an open network, open Wi-Fi network. This is the same way that Sainath connected to his network early on when we started this session. Then the concept came early on in the base standard. They implemented this mechanism called WEP, or it's also called as wired equivalent privacy. So inherently speaking, Wi-Fi is a little bit or a lot more insecure than wired network, just because of the physical nature of wireless, right? So for example, if this device is connected to this device and it is connected using a cable or a wire, then when he's communicating with him, I cannot tap into that at all unless I'm connected to some form of switch that's on the same network, physically on the same network. But in the case of wireless, it's wireless between this device and this device. So all I need to do is I need to bring some other device which is in the range of this communication. Let's say I'm in a bank and I'm trying to connect to the access point inside the bank. All the intruder has to do is they have to sit outside in the parking lot, and if they are in the range of the client connecting to the network inside a bank, then they are able to sniff the information and collect the data. So inherently speaking, wireless is more insecure than wired network. So they implemented this mechanism called WEP, or they called it wired equivalent privacy. So the idea is to actually create privacy that is equivalent to the one that you naturally get on a wired network. And so they implemented this concept of a WEP key, and then the key can be given to the client, and the key can be given to the access point. And now you first authenticate. Remember the example I gave you about Chris and Rob? They are first trying to authenticate each other. That's the first step. And so to do the authentication, you do something called as a shared key authentication. So now that the client and the AP both of them have the WEP key. So what the client will do is it will send an authentication request, and it will say, I'm using shared key authentication. And then the AP will say, okay, you're using shared key authentication. That means you must have a WEP key. So let me send you some basically a challenge text or a plain text. So it will send a bunch of text information from the AP to the client, and the client will take the information and it will encrypt it using the WEP key that you have here and send the encrypted information to the AP. So now the AP receives the encrypted information. Since the AP also has the same key, it will decrypt that information using that key and retrieve the plain text. And if it is able to successfully retrieve the plain text, then it knows that the client also has the same key, right? And it sends an acknowledgement saying that, yes, I'm able to successfully decrypt the information that you send me. So I trust that you have the same key that I have. So both of us have authenticated each other. The client and AP know that they have the same key, and then they will finish the authentication process. And then they will go to the confidentiality part, which is the encryption. Remember the example I gave about Chris and Rob? First, they need to mutually authenticate each other, and then once they authenticate, they will encrypt. So then for the encryption, you would use the same key again, and then you would encrypt the information. So this is how you would use WEP to actually do the authentication and the basic encryption part using shared key authentication. So what is a WEP key? Actually, let's talk about what is a key in very basic terms, right? So of course, we all know the keys that we have to like open our houses and cars and so on. But what does a key mean in the context of networking? So let's say you have some valuable some goods that you want to transmit. So what can you do? You can put it inside a safe like that has the digital lock, and then you can use a particular key for that. So in this particular case, a key is a combination of digits, right? Or that only the sender will know. The sender will know this combination. And so now the sender is going to send this safe to the receiver. And if someone is intercepting that safe somewhere in the middle, let's say the mailman who is carrying the case wants to see what's inside it, since that person does not have the key, they'll not be able to unlock it and get the valuable information. But the receiver, if he has the same key, somehow he got the same key, then he can unlock the box and get the valuable information out. So this is how keys are used, right? And if you take the plain text example of that, again, sender is sending clear text here, and then that is encrypted using the key, and you get the ciphertext, and then this ciphertext is transmitted, and no one else in the middle can decrypt it. And then on the receiver side, if the receiver has the same key, then it can do the opposite function and then retrieve the clear text. Now the sender and receiver are communicating successfully with each other, and they're able to understand each other, but no one else in the middle is able to understand that. So that is how keys work in security. So now let's get back to WEP, right? So WEP was the first method of security that was implemented. So it was introduced in the base .11 standard, as I mentioned, and it uses encryption keys to encrypt data and decrypt data. And the key is basically a sequence of either 40 bits or 104 bits that are represented in either 10 or 26 hex digits, right? And then if you're doing a 40-bit key, then normally the actual key length will be 64-bit, because we add another 24 bits in the front, and we call it as an initialization vector. And why do we need initialization vector? I'll talk about that in a second. And if you're doing a 104-bit key, then you have 128 bits, because you add another 24 bits as the initialization vector. So an initialization vector is nothing but a random stream of 24 bits that is changed for each packet transmission. And why is this important? This is important because remember that we are entering one key, just one web key inside the device, the access point, and the same web key here. And then we are using that web key to actually encrypt that the packet. So if there is an intruder, someone who is trying to basically hack onto this particular network, if they collect enough number of encrypted frames, right, and they use some form of a reverse logic, and if all frames or all packets were encrypted using the exact same key, then if you have collected enough data, then you can do some interesting math, and you can actually find the key if the same key is used to encrypt every packet. So to avoid that situation, what is done is, for every packet you use a random sequence of bits called the IV, and so every packet uses the base key, which is the same key, the 40-bit key or the 104-bit key, and it will add another 24 bits that are random bits that are changing for each packet. So that way the combination, either the 64-bit or the 128-bit combination, is a unique combination for each packet, right? So now the sender will encrypt using that unique combination, so which means that every packet that is sent from the sender to receiver is encrypted using a different resulting key, even though the base key is the same. So that is the logic, right, behind using the concept of initialization vector. So when you select the security mode as web in your access point, you can actually select the encryption type. You can see here 46 bits and or basically 64 bits or 128 bits. You can also enter the keys in hex, and in this particular access point, it allows you to enter up to 4 keys, and you can select which key you want to use basically as your key that you want for encryption, right? So this is how basically web is designed. Now, how does the actual encryption and decryption work using web? So first you have the plain text, and this is the information that you want to send. So the first thing you want to do on plain text is you want to check integrity on the plain text. Remember, we said that there are 3 parts of security: authentication, encryption, and message integrity. So first you need to ensure message integrity. So what will you do? You take the plain text and you calculate what we call as a checksum or a CRC on it, which is a calculation that results in a series of bits that you can append to the plain text. And when the receiver receives the same information, it will do the reverse calculation, and if the CRC matches, then the receiver knows that the plain text has not been modified, or there are no errors in the plain text. So CRC represents the message integrity check, right? Or it actually ensures message integrity. So first you calculate the CRC on the plain text and you append that, and then you start encryption. right? So how do you do the encryption? You take the 24-bit IV, which is unique for each packet. So let's assume this is one packet. So for each packet, you'll have a different IV, but the base key is the same, right? So you take the 24-bit and concatenate the base key, and then you run that through what we call as a RC4 algorithm, which is an encryption algorithm. And then the RC4 algorithm will create a key stream, which is basically the same length as the plain text plus the CRC, right? So now you have the key stream, and then when you have the key stream and you XOR it with the plain text, right, then that results in what we call as the ciphertext. So you take the key stream, which is a sequence of bits that is generated from the RC4 algorithm as the result of using the IV and the base key, right? And you use that and run that to the algorithm, and then you create a key stream, and then from the key stream you XOR it with the plain text and you create the ciphertext. This is what is being sent on the air. Now, along with the ciphertext, you also need to send the IV in plain text for that one particular packet. Remember that each packet has a different IV, right? Similar to the example I showed before, when you're actually sending the gold in a basically in a safe, and you're sending the safe to the other side. Similarly, you need to communicate the key, the IV, the IV here also to the receiver. On the receive side, what is happening is the receiver will take the IV that is part of this particular received message, and then it will take the base key. Remember that the receiver already has the base key. It does not have the IV for the packet, but it receives the IV in the plain text, right? So it takes that IV for the packet and the base key, and then again it will do the concatenation, and then it will run the same RC4 algorithm, and from there it will create the same key stream. And now it will do the exact opposite, where it will take the key stream and XOR it with the ciphertext that was received, right? And from that retrieves the plain text. And then from the plain text, and again you do the opposite of the CRC to make sure that the message integrity was there with the plain text, and there are no errors in the bits and bytes of the plain text. So this is how the encryption and decryption happen using web. So you only have the only requirement here is both the sender and receiver need to have the same base key that is already installed, and everything else is automatically taken care of by the system. Now, if there is an intruder, let's say even the intruder does not know the key and they don't know the IV. So if they have collected like 10,000 packets, one of the things, and they're trying to somehow basically crack the key. So for each packet, the resultant key is different because the IV plus key combination is different, and so it makes it a little bit harder for them to actually decode the key basically. But there are a number of flaws in the case of web, and the first one of the weaknesses is that web uses what we call as an RC4 stream cipher algorithm, which is considered to be relatively weak and easy to crack. And another major flaw with web is that the IV is only 24 bits long. So there is a 50% chance that the same IV is repeated after every 5,000 packets. So if there is a very determined hacker, and if they've collected like thousands and thousands and thousands of packets, then maybe there could be like 10, 20, 30 packets that have the same IV. And if they've collected enough number of packets that have the same IV, then they have a better chance of exploiting the data and basically retrieving and hacking and retrieving the base key. And once they retrieve the base key, then they can decrypt everything, right, very easily. So the web has its own set of flaws, and of course the other major flaw here is when I enter the key here and I'm using the same key to communicate between this client and this AP. So which means that every client connected to this access point will use the same key, which means that let's say my neighbor and I am using the same key to connect to this access point, then I know the key and they know the key. So they can actually act as a hacker and decrypt my information. So using the same key in the entire wireless LAN cell it's in itself a major security risk, right? Then came WPA. So because the web got cracked very quickly, and the people saw the flaws in web, so the standards body tried to patch up and use this mechanism called Wi-Fi Protect Access, or WPA, and it was intended to provide better security over web, but it was not intended for long-term use, and it was actually a temporary solution, because they didn't want to change the hardware configuration. They didn't want to change the hardware. They just wanted to be basically a firmware upgrade from web to provide better security. So it is still basically it released an intermediate solution to overcome the weaknesses of web, and it uses something called as a TKIP or Temporal Key Integrity Protocol, which is also based on RC4, right? But it is a lot more robust, and it uses 48-bit IV instead of 24 bits. So which means that the chances of an IV repeating is much lesser when compared to the 24-bit IV. And it also uses 128-bit keys for encryption, right? Which is longer, now having a longer key length for encryption ensures more security. So it's basically a base firmware upgrade from WPA to web. And if you look at what improvements it provides over web, one of the major improvements is it creates multiple layers of key generation. So what it does is it takes the base key that we provide, and then from that it creates session keys. So then that means that for every packet there is a new encryption key that is generated for each packet, and that makes it even more secure. And of course the 48-bit IV instead of 28-bit makes it more secure. And then the other thing that the WPA does is it actually uses the transmitter's MAC address in the key generation, right? So even though there is the same base key, remember I talked about a problem with the web. If you know the password, if my neighbor knows my password, then both of them are using the same key to encrypt, and so that's a problem. But in the case of WPA, the actual key that is used, which is derived from the base key, and it is derived using the transmitter's MAC address, which means that the actual key that is used between my phone and this access point is different from the key that is used from a different phone to the same access point. Even though the base key is the same, the derived keys are different because they are derived based on the device's MAC address, which is unique to that particular device. So it adds another layer of security there as well, right? And then the data integrity, it also uses something called as the message integrity check function, which is again a much more robust mechanism of doing message integrity than the CRC method. So in the interest of time, I'm not going to go into all the details here. It's again, there's lot to read here, but at a very high level, if you look at how the WPA encryption procedure works, the key mixing is done in multiple phases. So you basically take the base IV, which is much longer, you break it down into components, and then you take the transmitter's address, which is the transmitter's MAC address, and then you use them and use a particular mixing technique to generate the phase 1 keys. And then from the phase 1 key, again you take the keys that are generated here, and then from there you use another level of phase 2 mixing, and then you generate the phase 2, do the phase 2 mixing, and then from that you basically generate the seed key, which is again based on the original base key plus all the derived keys that are created. And that web seed is now fed into the RC4 algorithm, which is basically which actually then creates your key stream. And this key stream is so unique that it's for every packet, for every session, for every device, it's a completely unique stream. Even though if you crack one key stream for one packet for one device, then the next key stream for the next packet for the same device is completely different. So that actually makes it a lot harder to decode. So now you use this method to create the key stream. On the other side, you do the integrity, where you take the plain data and then you actually take the source address, the destination address, and all these things, and you compute the message integrity check function. And then from there, you actually create the data stream that you're going to transmit. The data stream is going to have the message integrity and something called as the integrity check algorithm details. And then you take the plain text here, and then the key stream here, and then you do the same XOR function, and then from that you generate the encrypted data here, which is basically your ciphertext. And this encrypted data has the base plain text plus the message integrity check plus the ICV, and then you put that inside this header. There's a MAC header, and then you also have another layer of FCS, and then you transmit this. So there's a lot of extra overhead that is added, but every overhead that is added adds another extra layer of security, right? So the integrity is much more secure, and then the encryption is a lot more secure as well. We don't have the time to go through all this in detail, but again, all of this is in the references section. You can go learn more about this, and there are lots of really good tutorials available online if you want to understand all the calculations behind this. So that's WPA, and of course WPA also had its own set of flaws, and people were these algorithms were created by humans, so of course they can be hacked by humans also. So WPA also had its own set of flaws and set of attacks. So after that, the standards body came out with the WPA2, which is a complete redo of security. So they stopped doing the base RC4 based encryption, and they went into this AES encryption, which is also referred to as Advanced Encryption Standard, which is the most advanced method of encryption that was there at that time, and it was used for military applications, right? And because military applications is where you need the most security, so AES was considered to be one of the most robust mechanisms that uses this concept of block ciphers, and it has a much better way of doing authentication, encryption, and also message integrity, right? And use for authentication we use this AES CCMP. For encryption we use AES CCMP mechanism, and then you also have better integrity, right? In the interest of time, I'm not going to go into all the details here, but what we can see here is when you log into your access point, now you can select WPA and WPA2 PSK or pre-shared key methods. This is for residential use where the keys are entered ahead of time, right? And then you can type in the key here, the base key, which is again used to create all the session keys and the temporal keys and all of that. And then you can select the security type. So one of the things WPA2 APs allow you to do is they allow you to be backward compatible. So you can choose a method which says WPA2 PSK and WPA PSK, which means that if one of my devices can connect using WPA2, maybe another device that doesn't support WPA2 can connect using WPA. Because remember that WPA2 requires hardware change. It's not just a firmware upgrade from web. It needs hardware change. So not all hardware can actually, because it's a lot more computation intensive algorithm, so it requires better hardware, right? And because of that reason, it's not directly backward compatible. So to enable backward compatibility, most APs will support a combination of WPA and WPA2, which means the WPA2 device can connect using WPA2 and a WPA device can connect using WPA. And then after many years, after a long gap, the industry came out with this concept of WPA3, which is supposed to be even more secure than WPA2. It uses even more newer encryption mechanisms, and it uses longer keys. It uses a even better message integrity mechanism, and it even WPA3 even introduced the concept of encrypting open connections. So even when you're doing open security, when you're connected to the in the airport, you're connected to the open Wi-Fi network, WPA3 will allow you to encrypt that also, right? And there's this new mechanism called OWE for that. And also WPA3 introduces this concept of protected management frames. So remember, when we're connecting to Wi-Fi network, we use probe requests, authentication, association requests. Those are all management frames, and those management frames are not encrypted. Only data frames are encrypted. So if you are not encrypting the management frames, people can launch attacks. Hackers can launch attacks on management frames. For example, a hacker can hack or use the MAC address of your device and send a deauth message to the access point, and that will deauth your client, right? So if it is the deauth messages are going in plain text, then it is very easy to basically create what we call as a denial of service attack, where a hacker can deny service to you by deauthing on your behalf, right? So if you don't have the management frames protected, you're vulnerable to those kinds of attacks. So WPA3 introduces this concept of protected management frames, where you can encrypt the management frames also, and then it also provides much better methods that would protect people from offline dictionary attacks and things like that. So there are a number of advantages for WPA3 also. I put some references in the links in the references. So if you want to study more about that, you can certainly do that. So so far we talked mostly about the personal security, where you have to manually enter the keys into the access point in the client device. It could be using web, it could be using WPA, WPA2, WPA3, and so on. But when you come to the enterprise, that's not how security is done. Even though we're still using WPA, WPA2, WPA3 for encryption between an access point and a client, the authentication is done in a different way. And that is where we have the authentication server that comes into the picture. And there is a whole mechanism for authentication, and there is a concept of certificates, and the client, the device needs to have certificates, authentication server needs to have certificates, there has to be mutual authentication using certificates, and so on. We'll go into that in more detail in the next session and explain how enterprise security will do authentication, and from the authentication, how will it generate keys. So you're not manually entering keys anywhere at all, right? The keys are auto-generated, both on the transmitter side and the receiver side, and then those keys are then used for encryption. So how that process works on the enterprise side, we can go through that in more detail in the next session. So to summarize, in Wi-Fi security that we know, normally there is the standard called WPA. Under that, we have like just base web, and then we came then they came up with WPA, which is a patch up for web, the flaws of web. And then after a few years, we came out with WPA2, and then there's WPA3. And then these mechanisms can have both the personal version, where you're using it in residential networks, and they also have enterprise versions, where you're using them on a enterprise network, right? And you use different methods to do the authentication. So if you look at this particular table, you can see when these standards were introduced. The web was introduced in 1999 with the base standard, and then only about 3-4 years it took for people to crack the web keys. So then to mitigate that problem, WPA came out in around 2003, and then immediately afterwards there was WPA2 that came out. But then afterwards it took a really long time, because WPA2 was quite secure, and it was doing the job. It was not perfect, but it was doing the job. So they did not really bother to extend that. But eventually, after many years, fairly recently, about 4 or 5 years back, the WPA3 standard was introduced. And you can see the different encryption mechanisms. Web and WPA were using the RC4 mechanism, stream cipher, and then WPA2 and WPA3 went to the AES, which is more of a block cipher, more robust way of doing the encryption. And as we went through the standards, the number of bits that are in the key also started increasing. We started with 40 bits, but then we went to 128 bit and eventually to 192 bit in the enterprise side. The data integrity also started getting better and better with more complex algorithms. The key management and authentication also got better and better. And then as we went through WPA3, now you not only are encrypting data frames, but you're also encrypting management frames. You're also encrypting open connections, open security connections, and so on. So it's making the security more and more robust as we go. So that's a quick overview about the various security standards. There's also this other method that people have been using for a while. It's in most cases it's not used anymore. This is called this Wi-Fi protected setup, or WPS, which is a physical way of creating security. Most old routers should have this. Let me check if this one has. Yes, so this router also has the WPS. So I'm not sure if I can show it here. But if you look at there's a button here, a physical button on this access point on this router. When you push this button, and when this router is on, you're turning on WPS, which means that any device that is closer to this particular Wi-Fi router can automatically connect to it based on proximity, right? Because of this access point is right next to the device. So this is one way of doing secure connection, and this will work even with when you have WPA, WPA2, and all these other security methods enabled. And it relies on the fact that the device is very close to the access point, which means that it must be a secure device, and it must be a valid device. And that is the idea about WPS. Of course, WPS has a lot of flaws as well, and because of that, that method has not been used much. Okay, so we covered a lot of ground, and a lot of this can be quite confusing. So, and again, it's hard to cover all the details in one session. But we're going to end this session by giving you some tips on how to secure your Wi-Fi network, at least in the home. How could you secure a Wi-Fi network, right? So what do you do? Of course, you need to update your router to use the latest encryption mechanism. We all learned today that open authentication is not at all recommended, and then all these other security methods. The more advanced security method you use, the better security you have. So of course, try to upgrade your router to the latest encryption mechanism. Change your password, router default settings, usernames and passwords. If a hacker hacks into the account of this router, they can actually log in, and if they're using the same default username password, they can log in, and then they can change the SSIDs, they can change everything, right? So of course, change your router default settings. Use strong security keys and keep changing the keys frequently. Turn off features like WPS and universal plug and play and things like that that will make your devices less secure. Turn on any firewall settings that you have in your router. Select the safest possible location for the router in your house, so that physical based attacks, tampering of a physical device is not going to happen. And then set up a separate guest network for your guests, so that they have restricted access and they're not tampering with your private network. And then turn on access control lists and MAC address filtering. So for example, let's say there are 10 devices in your house and you know the MAC address of each of these devices. You can create an access control list, and you can tell the router only admit traffic from these 10 MAC addresses and don't admit anything else. And that's a very nice way of securing the network, until someone spoofs your MAC address, then you have a problem. But assuming that no one spoofs your MAC address, then you can get security that way by just listing the only admitted MAC addresses on your network. Right? And log out of the router's admin mode, update router firmware regularly, so that you get the latest patches when it comes to security. So these are some of the methods in which you can secure your Wi-Fi network in your home. So we covered a lot of ground. We talked about the pillars of Wi-Fi security. We talked about the enforcers of Wi-Fi security. We talked about the base web standard, how it evolved to WPA, WPA2, WPA3, and so on. And then we covered about how to secure your Wi-Fi network in the house. And these are some of the topics for today. Of course, we'll get into a lot more detail in the next session about enterprise security and how that works. Here are some of the references for today's session. Hope you found this session useful. Over to the moderator for Q&A.
Yeah, it is a great session. So as you were discussing about the encryption, so initially I was connected to an open network, and as the session is going on, I switched it to WPA2. And then I tried to browse the same HTTP website, which I showed it at the start of the session. So I think since I'm using WPA2, I hope even if somebody captures over the air, I hope I'm still safe, because there is AES encryption happening, right?
Hold on, Sainath. Do you really think you have connected a Wi-Fi network?
Yeah, because there is WPA2 encryption, right? So I think
I did something while you are connecting to a Wi-Fi access point, and let me show you that.
Okay, seems like this guy has done something over there. Let's see what he has done.
So what I have done here is, so I captured his data while he's connecting to Wi-Fi network to Candle office, where he says WPA2 is enabled and he thinks he's secure. So I have captured, and you can see all here, the data is from his laptop. Okay, and you can see the connection process. He connected, and you can see the association response request, and you can also see he connected to PSK, which is SHA-256, means that is WPA2 personal. Also, after that, he generated the keys to encrypt the data. So after this 4-way handshake, you can see the QS data. See, here is a broadcast message, and it is encrypted. I can't able to understand what this data means, right? So because it is encrypted using WPA2. Yes, Sainath, you said that you're correct, and I can't see your data, but I'm an employee of this company, right? So I have the same keys, same password that you're using, right? So our IT admin gave the same password to me as well. So let me use the same key to decrypt this data and show what you did while you in the HTTP process, right? Okay. Let me go to edit, and here preferences. And if you expand these protocols, let's just search for IEEE 802.11. Okay, yeah. Here you can enter your keys. Okay, here I will enter the keys that I have where he has connected. Okay, this is the password and this is the SSID. Okay, I have entered, and let me just click OK. And okay.
Oh no, looks like you cracked the encryption. I can
Yeah,
the
this is called after he generates the key, he sent a DSCP discovery message to get an IP, and I hope I can also see his HTTP data if he browse. Okay,
So
let
you
me
are
just
saying you can see the website that I visited?
yeah, I think so. If you did, yeah, see
Oh, no.
you get into some login websites. Are you kidding? Okay, what is this data? Oh, you did the same test again, right? So now, yeah, see, I can see your text password, text username that you shared. I think you also visited some other websites. Can I open?
Yeah, you can.
Right. Okay. Let's just open this post URL, and you I think you tested on different website to show the demo. And okay, here is some information that you provided. Oh, some username, some details. Yeah.
could see a lot of data.
Yeah. So are you also using same WPA to personal? And do you really understand the difference between personal and enterprise? And do you want to know more about how you can secure a network? We are going to show you all these things in the upcoming session. Please, please join, and I hope you will all enjoy this session. Okay.
Please don't share your Wi-Fi passwords to others if you don't trust.